Hello everyone, myself Hinasha. So today we are going to discuss few topics of complex numbers. So let us start with the Moivre's theorem. For any real number n, one of the values of cos theta plus I sin theta whole raised to n is cos n theta plus I sin n theta. That is, we can write this as cos theta plus I sin theta whole raised to n will be equals to cos n theta plus I sin n theta. Very important theorem. Fine. Now, similarly, what we can say, cos theta plus I sin theta whole raised to minus n. So we know using Euler's formula, this can be written as e raised to I theta whole raised to minus n. Now we can write this as e raised to minus n I theta. Right? Now this can be written as cos minus n theta plus I sin minus n theta. But sin is an odd function and cos is an even function. So finally this can be written as cos n theta minus I sin n theta. From these two, what we have derived, that cos theta plus I sin theta whole raised to n is cos n theta plus I sin n theta. And if here it is minus n, the formula will be cos n theta minus sin n theta. Next, if we take the conjugate cos theta minus I sin theta whole raised to n, right? Now this can be written as e raised to minus I theta whole raised to n. This can be simplified as e raised to minus n I theta. And we can write this as cos n theta minus I sin n theta. And what is this equal to? Cos theta plus I sin theta whole raised to minus n. So if here we write z bar whole raised to n, it is equals to z raised to minus n. From this we have derived this identity. Okay. So now let us study few remarks. So if z is equals to cos theta plus I sin theta, then 1 upon z will be equals to 1 upon cos theta plus I sin theta. Now this can be written as cos theta plus I sin theta whole raised to minus 1. Just we have studied one property, right? So this can be written as cos theta minus I sin theta, okay, which is equals to z bar. So this we have derived using this z bar whole raised to n is equals to z raised to minus n. You can see here z raised to minus 1 is equals to z bar, right? So this is an important criteria. Now we cannot write cos alpha plus I sin beta whole raised to n, right? This is not equal to cos n alpha plus I sin n beta. Similarly, sin theta plus I cos theta whole raised to n is not equals to sin n theta plus I cos n theta. But we can find the value of this using some minor modifications. So sin theta plus I cos theta whole raised to n can be written as this sin theta. We can write it as cos 90 minus theta, that is cos pi by 2 minus theta. And cos theta can be written as what? Sin 90 minus theta. So we'll substitute this. So sin theta can be written as cos pi by 2 minus theta plus I. Cos theta can be written as sin pi by 2 minus theta, and here we have whole raised to n. Now using the theorem, we can write it as cos n pi by 2 minus theta plus I sin n pi by 2 minus theta. Now take this n inside. So finally sin theta plus I cos theta whole raised to n is equals to cos n pi by 2 minus n theta plus I sin n pi by 2 minus n theta. Okay. So now let us find nth roots of a complex number. So if we have complex number z is equals to x plus iy, and I want to find its nth root, that is z raised to 1 upon n. So that will be equals to x plus iy whole raised to 1 upon n. Now we'll convert this in polar form. So we can write it as z raised to 1 by n is equals to, we'll replace x by r cos theta, y by r sin theta, right? So r times we will have cos theta plus I sin theta whole raised to 1 upon n. Now just modify this as z raised to 1 by n is equals to take r outside. R raised to 1 by n cos theta plus I sin theta whole raised to 1 upon n. Now we'll replace theta by 2k pi plus theta. So just here in place of theta write 2k pi plus theta. So your z raised to 1 upon n will be equals to r raised to 1 upon n into cos 2k pi plus theta plus I sin 2k pi plus theta whole raised to 1 by n. Now we'll apply over here in this bracket the Moivre's theorem. So z raised to 1 upon n will be equals to r raised to 1 upon n into cos 2k pi plus theta upon n plus I sin 2k pi plus theta upon n. So this is the formula to find nth roots of a complex numbers. Now let us one by one put the values of k which are 0, 1, 2, 3 up to n minus 1. So now in this formula if I put k as 0, what will remain? R raised to 1 upon n cos theta by n plus I sin theta by n, and I will make the first root as what? Z0. Similarly put k as 1, so I will get z1 as r raised to 1 upon n cos 2 pi plus theta upon n plus I sin 2 pi plus theta upon n. Similarly put k as 2, so here we will have 4 pi, right? And so on. Let us put k as n minus 1 in order to find the nth root. So z n minus 1 is equals to r raised to 1 upon n cos 2 times n minus 1 pi plus theta upon n plus I sin 2n minus 1 pi plus theta upon n. Okay, so next let us solve examples. So we have to show that if C is the nth root of unity, so now our complex number Z is 1, right? Other than unity itself, then 1 plus C plus C square plus E raised to n minus 1 is equals to 0. We have to prove this. So now our complex number Z is given as unity, that is 1. So then let us compare this with x plus I. So from this we can write that x is 1, y is 0. Now in order to convert it into a polar form, let us find the value of r. Formula is square root of x square plus y square, that is square root of 1 plus 0, so the value of r is 1. Now both are greater than 0, x and y. So lies in the first quadrant, right? So now theta will be equals to what? Tan inverse mod y by x, that is equals to tan inverse 0. So answer is 0. So value of theta is 0. So in polar form, z is equals to, formula is r times cos theta plus I sin theta. Just put the values of r and theta. So finally z will be equals to cos 0 plus I sin 0. Okay. This is the polar form of our complex number. Now we want to find the nth root of unity. That means we want to find z raised to 1 upon n, that is 1 raised to 1 upon n. Now we know the formula of z raised to 1 upon n, general formula, that is r raised to 1 upon n into cos 2k pi plus theta upon n plus I sin 2k pi plus theta upon n. Fine, this is the formula. We know every value. Now we know z raised to 1 upon n is what? 1 raised to 1 by n. R is 1, so this is 1. Now the value of theta is what? 0. So what will remain? Cos 2k pi upon n plus I sin 2k pi upon n, where our value of k varies from 0, 1 up to n minus 1. So now we know that the roots of unity are C, right? Denoted by C. So let us start finding the roots of unity. Now let us put the values of k from 0 to n minus 1 in order to prove this, right? So if I put k is equals to 0, answer will be what? 1. Now let us put k as 1. So here if I put k as 1, we will get cos 2 pi by n plus I sin 2 pi by n, and this can be written as what? E raised to I times 2 pi by n, and I will name this as c. Similarly, if I put k as 2 in this, we will get cos 4 pi by n plus I sin 4 pi by n, and this we can write it as e raised to I 4 pi by n, and further I can modify this as e raised to 2 times 2I pi by n. So I can write this as c square, and so on. Lastly, let us put k as n minus 1. Fine. So our answer will be cos 2n minus 1 pi by n plus I sin 2n minus 1 pi upon n. Right? So these can be written as c raised to n minus 1. Now let us add all these nth roots of unity. So what we will get? 1 plus c square plus n, so on c raised to n minus 1. Now we know geometric series sum Sn is given as a into 1 minus r raised to n upon 1 minus r. Here you can see that the value of a is 1 and the value of r is what? C. So let us write. So Sn will be equals to 1 minus c raised to n upon 1 minus c. Now we are given in the question that the nth root of unity is denoted by c. 1 raised to 1 upon n is equals to c. Therefore, c raised to n is what? 1. So from this we can say that our answer of Sn is 0. Hence we have proved that 1 plus c square plus c raised to n minus 1 is 0. Okay, so now let us go to the next example. If alpha and beta are roots of this given equation, we have to prove that alpha is to n plus beta is to n is equals to 2 raised to n by 2 plus 1 into cos n pi by 4, and then we have to deduce that alpha is to 8 plus beta is to 8 is 32. So firstly, let us first find the roots of the given equation. So the formula is what? X is equals to minus b plus or minus under root b square minus 4ac upon 2a. Now here we can compare this with ax square plus bx plus c is equals to 0. So our value of a is 1, b is minus 2 and c is 2. Let us put all these values in this. Therefore, value of x will be 2 plus or minus under root minus 2 square means 4 minus 4 into 1 into 2, so 8 upon 2. So finally our x will be equals to 2 plus or minus under root minus 4 upon 2. That can be written as 2 plus or minus 2i upon 2, because square root of minus 1 is what? Plus or minus I. Okay, now take out what? Common 2. So your final values of the roots of the given equation are x is equals to 1 plus or minus I. Now let us name alpha as 1 plus I and your beta as 1 minus I. Now let us convert these two into exponential form. So first let us find the value of r. That can be obtained using the formula square root of x square plus y square. You can see x is 1 and y is also 1. So your r will be root 2 and theta will be tan inverse y by x, because x is 1, y is 1. So it lies in the first quadrant. So tan inverse what will come? 1 with theta is equals to pi by 4. Now, so final exponential form of alpha will be r e raised to I theta, where r is root 2 and theta is pi by 4. Right? So we have obtained alpha as root 2 e raised to I pi by 4. Now similarly, let us convert beta in exponential form. So x is 1, y is what? Minus 1. So this lies in the fourth quadrant. Okay. So First, r will be equals to 1 plus minus 1 whole square, so it will be equals to root 2. Now the formula of theta will be minus tan inverse mod y by x. Why? Because it lies in the fourth quadrant. So theta will be equals to minus tan inverse of minus 1, that is minus tan inverse of 1. And so theta is equals to finally what? Again minus 5 by 4. So write the exponential form using this formula. So beta will be equals to root 2 e raised to minus I pi by 4. Now let us find the value of this. So now alpha raised to n plus beta raised to n will be equals to root 2 e raised to I pi by 4 whole raised to n plus root 2 e raised to I minus I pi by 4 whole raised to n. Just put the values of alpha and beta. Now we can take out common what? Root 2 raised to n. So inside what remains is e raised to I pi by 4 whole raised to n plus e raised to minus I pi by 4 whole raised to n. Okay. So now we can write this as 2 raised to n by 2, right? And inside we can modify this as e raised to n pi by 4 I n pi by 4 plus e raised to minus I n pi by 4. Now using Euler's formula we can simplify these two as 2 raised to n pi by 2 into cos n pi by 4 plus I sin n pi by 4 plus this can be written as cos n pi by 4 minus I sin n pi by 4. Right, now these two gets cancelled out. So we are getting 2 raised to n by 2 into 2 times cos n pi by 4. So finally we have obtained our desired result, that alpha is to n plus beta is to n is equals to 2 raised to n by 2 plus 1 cos n pi by 4. Okay, now we have to obtain the value of alpha raised to 8 plus beta raised to 8. So in this result put n as 8. So you will get alpha raised to 8 plus beta raised to 8 as 2 raised to 8 by 2, right? So it will be 4 plus 1. So 2 raised to 5 into cos, if I put 8, it will be 8 pi by 4, that is cos 2 pi. Now we know the value of cos 2 pi is what? 1. So what is remaining? 2 raised to 5, answer is what? 32. Hence we have proved our desired result. Now next example, using de Moivre's formula, we have to find all roots of 8i raised to 1 upon 3 in the complex plane. So now let us convert our complex number z is equals to 8i into polar form. So compare it with x plus iy. So your x is 0 and y is what? 8. And we know this lies in the first quadrant. Fine. So now let us obtain the value of r. So formula is square root x square plus y square. So square root of 0 square plus 8 square. So the value of r will be 8. And it lies in the first quadrant. So formula of theta is tan inverse mod y by x. So tan inverse we will get infinity, and so value will be 5 by 2. Now in order to find nth roots of any complex number, formula is z raised to 1 upon n. That will be equals to r raised to 1 upon n cos 2k pi plus theta upon n plus I sin 2k pi plus theta upon n. So just put all these values, right? So your 8i raised to 1 upon 3. So the value of n is what? 3. Will be equals to 8 raised to 1 upon 3. Put over here the value of theta. So cos 2k pi plus 5 by 2, right, upon n, that is 3 plus I sin 2k pi plus 5 by 2 upon 3. Right, now finally let us simplify this. So now let us take LCM in this bracket. So final answer will be 8I whole raised to 1 upon 3 is equals to 2 times, take LCM, so cos 4k pi plus pi upon 6 plus I sin 4k pi plus pi upon 6. You can take pi common also, right? Now if we put the values of k as 0, 1 and 2, we will obtain the required roots of our given complex number. Okay? So in this you have to put the values of k as first 0, then 1 and 2, and you can find the roots of 8I raised to 1 on 3. So now let us go to the next example. We have to solve z square minus 5 plus I times z plus 8 plus I is equals to 0. Just we have to find the roots of this given equation. So it is very simple. Z will be equals to what? Minus b plus or minus under root b square minus 4ac upon 2a. Compare with az square plus bz plus c is equals to 0. So your a will be what? 1, b will be minus 5 plus I, and the value of c will be what? 8 plus I. So let us put all these value in this to find the roots of z. So z will be equals to 5 plus I, right? Plus or minus under root of 5 plus I equals square minus 4 into 8 plus I upon 2. Okay, now let us simplify this further. So this can be written as 5 plus I plus or minus, open the bracket as a plus b whole square, a square plus 2ab plus b square. So here it will become 25 plus 10I plus I square minus 32 minus 4I upon 2. Now we know that I square is what? Minus 1. So here this will go to minus 1. So let us simplify and write it. So 5 plus I plus or minus under root. What will remain? 25 minus 1 minus 32. Okay. And here we will get 10I minus 4I. So it will be 6I minus 8 upon 2. So now what we will do is, firstly we will modify this minus 8 as 9I square plus 1. Okay, why? Because we know I square is equals to minus 1. So this is minus 8. In order to make this term inside the square root as a perfect square. So now let us write that. So z will be equals to 5 plus I plus or minus under root of 9I square plus 6I plus 1 upon 2. Okay. Now this is a perfect square of 3I plus 1 whole square upon 2. Okay. So now this can be written as 5 plus I plus or minus 3I plus 1 upon 2. So now first root will be 5 plus I plus 3I plus 1 upon 2. So alpha will be equals to what? 4I plus 6 upon 2. So answer will be 2I plus 3. Now for beta, let us subtract. So 5I minus 3I minus 1 upon 2. So it will be what? 4 minus 2I upon 2. So answer finally is 2 minus I. So these are the two roots of our given equation. Okay. So I hope you have understood throughout the session. Thank you for watching.